So welcome everyone to today's seminar. Today we have Professor Claudia Maraston from the University of Portsmouth in the UK, and her main field is galaxy formation and evolution. She obtained her PhD at the University of Bologna in Italy. And after her PhD, she was a research fellow at Munich in Germany, and then at the Max Planck Institute for Extraterrestrial Physics, also in Germany, before joining the University of Oxford in the UK as a Marie Curie Fellow in 2005. In 2007, she received an Excellence Team Research Grant from the European Research Council, with which she joined the ICG at the University of Portsmouth. Claudia Maraston is an expert in evolutionary synthesis population models, and many other things. And she has been a visiting scientist in multiple institutions. And she has co-authored more than 230 papers in peer-reviewed journals. Claudia, thank you so much for accepting our invitation. I think you've been here to Rio Grande do Sul, but not formally to our university yet. Sorry for the slight delay with the technical problems, but now the floor is yours.
Thank you very much, Anna, for this kind invitation. And I've already seen Rosario, and I know all of you guys. So let me start by sharing my screen. To see whether this works. I should probably share. Okay, you can see the screen for sure. Okay, does this work?
Yes, perfect.
Perfect, so I can get started. I cannot see my cursor, so when there are features, I will have to describe them by hand. So the title of this talk, this counts really a lot to me, but also to your community. It's something that happened quite serendipitously last year. And the title is The Detection of a Particular Stellar Phase Imprinted on the Spectra of High-redshift Galaxies. And I will make clear what 20 years later means. So as Anna was saying, the grand context of this work I'm doing, and many of you are doing as well, is to try to understand the processes underlying galaxy formation and evolution in a universe that started with a Big Bang, expanded extremely fast, and after actually a short time started to form the very first stars, and the very first stars coalesced in the first galaxies. And then the vast majority of the lifetime of the universe is actually taken for galaxy formation and evolution. But galaxy formation and evolution is a very complicated process that entail a lot of occurrences that are actually still at the present time parameterized with the fudge factors or with the exact parameters at best. In particular, the conversion of gas into stars is something that we still don't know exactly how it happens. The feedback from stars and the massive black holes that was actually, again, introduced basically 20 years ago in 2006 in order to explain why the most massive galaxies are the oldest. If we accept to live in a universe dominated by dark matter, then mass growth due to dark matter merging has its own uncertainties. And more recently, people are actually trying to understand why star formation stops. This is called quenching, because indeed there is always emission of gas from stellar evolution, and somewhat is unclear why the star formation is quite a non-efficient process. So all these complications are dealt with by obtaining what we call the physical properties of galaxies at increasingly high cosmic distances. And to show this, I, of course, use the latest deep field observed by the James Webb Space Telescope, which is absolutely beautiful. For those of you that have a certain age, we have seen the HST deep field, but this one is even more stunning, which shows actually as a function of look-back time how this galaxy work. But they are beautiful colors, but with this, we don't do much astrophysics. What we need are the physical properties. Also including the distance, so redshift, but then age and formation epoch, the star formation history, the chemistry, the mass in stars, which will allow us then to obtain the information about the dark matter, and more recently, the mass in remnants, which are actually sourcing gravitational waves. So how can we astronomers obtain these properties? By using theoretical spectra that are calculated as a function of the parameters we would like to obtain. The first and foremost is the age of this stellar generation, the chemical composition, and all the alike. And having a suite of spectra and compare to data is the classical way in physics to obtain a certain information. Theoretical ACD of stellar population models are a good field to work because they are actually used in a wide variety of astrophysical investigations. And now show a plot from my work in which you show the predicted luminosities as a function of wavelength from the UV to the near infrared where stars are dominant. Obviously, in the far infrared, we have emission, but it's not due to stars, and also a short wave. That's the main place, the main location in wavelengths where we can hope to obtain the physical properties of galaxies. And then you see spectra. Several of you will be familiar with this, but in case there are students, and now they actually change from the youngest population that you see in the top left from my screen, maybe the opposite for you, 1 million year population with a lot of UV emission, and then an evolution that lasts 10 billion years will remove, without adding star formation, will completely remove emission in the UV, while the near infrared is relatively unevolving in this sense. So this is a basic prediction without any dust emission, something like how stars emit their light while they are evolving and ultimately die. So the technique that allowed us to calculate theoretical spectra with a predictive power is called evolutionary population synthesis, and I need to acknowledge the fundamental contribution from Beatrice Tinsley to the theory underlying assembling stellar population theoretically in order to make prediction on a cosmological scales. In fact, I only show two photos in this sense. One is from Beatrice Tinsley, and the paper 1972 was the first paper that I was given to read as a PhD student. And then Alvio Renzini, who was also my supervisor, who in 1981, shortly after Beatrice passed away, defined something very important that I use in my model, which is called the fuel consumption theorem. And that's why I'm showcasing these two images also because you need to be careful also to show images of other people, but I would like to acknowledge the immense work by Gustavo Brusual, who is in South America, and Charlot in the term of these models. So focusing on what we calculate, the fuel consumption theorem, which is quite central to the things I'm going to tell you today, establish an analytical relation to be able to weigh evolutionary phases of stars, directly connecting them to the energetics in the core or in the shells of their stars while they evolve. Because ultimately, the light that you can squeeze out from stellar phases must be directly proportional to the amount of hydrogen or helium that those stellar phases will be using up in their nuclear burning. And this is what is the fuel consumption theorem. And so if you work with this type, in this framework, you can actually divide the evolutionary lifetime of a stellar population. Note that when I say stellar population, for me, that's a galaxy. So of a theoretical population into 3 periods, essentially. Young population will be dominated by the core helium burning as a post-main sequence phase. All the population, you see this in the graph, will be dominated by red giant branch phases. And then there is an intermediate period that has been much controversial in the literature and is basically the main actor of this talk today, where actually most of the light in post-main sequence phases comes from a short but luminous phases that we call the asymptotic giant branch. And I'm going to come back on that. Obviously, the other main energetic contributor are stars on the main sequence because that's where most of the population will be. So knowing this, you actually try to model complex galaxies. Obviously, this model were immediately thought for things that are far away. You don't use population synthesis for the Milky Way, where you can actually resolve stars. In their location, you use other technique. So this is the integrated light problems, where you have essentially one information encoding all the stellar phases of the stars. And again, I use an historical plot to visualize what I mean, which is known as the PIG, published by Arenzini and Buzzoni in 1996, where they were saying that a good galaxy model requires a careful account of all evolutionary phases because they all may have a contribution to the energetics, and in integrated light, you are not going to be able to dissect it. So you have to put it into your models. I still like to show this type of plot. So let's come to this particular evolutionary phase, which in extension is called the thermally pulsating asymptotic giant branch. In this plot, I show you an HR diagram in the observed framework, but where I have identified all the critical stellar phases. And you see that the asymptotic giant branch is occurring at red colors means cold temperature and very bright luminosities. It is indeed the last luminous phase before the evolution into planetary nebula and white dwarfs of intermediate mass stars. This phase, however, has been the big elephant in the room of both the stellar evolution and the galaxy evolution modeling because of the intrinsic difficulty in modeling the phase due to its internal structure. The internal structure, and that's why it's called like this, is of a double shell burning in alternation, and that's why it's called pulsating. And essentially, when the helium, the very inner helium burning shell is active, the emission of luminosity causes expansion of the stars, which quenches down the hydrogen shell burning. The stars will then be forced to recontract, and that will increase temperature and density and restart the inner shells. This leads to a pulsation that is very hard to model, first for computational time, still nowadays, but also because during the pulsation, the stars is losing mass. And mass loss is another one of those problems in astrophysics for which we don't have a first principle theory. So the high luminosity and the short the duration plus the strong mass loss made it such, was always the most tricky evolutionary phase to model. And I would like to acknowledge in this respect the massive work performed by Paola Marigo and collaborator at Padova, especially because unfortunately Paola Marigo passed away a few months ago. So essentially for this stellar phase, the main things that we know that we want to have to model the spectra, that are the energy per stellar mass and the spectrum itself, are quite uncertain. I spoke about the energetic, but please let me show you how the spectra of TP-AGB stars look like, taken from the classical work by Lanson and Moussin. But these are good spectra because they are after the near infrared that are also input to my model. So the left-hand side show a carbon-rich star spectra, and the blue and the red display two different approximate spectral types, so where the ACD will peak, the blue being relative to warmer temperature, obviously, and the red to colder temperature. What you see are these deep bands originating by several compounds, specifically of carbon, actually CM bands. To the right, you see oxygen-rich stars. They are called like this because they are featured by absorption of oxygen species, CO and titanium oxide, and vanadium and other things. And again, I actually quote the two extreme spectral type of this work. So not only the stellar evolution is complicated, but also the model atmosphere. We know from the work of Kurukt, people have modeled in detail with the Saha function, the atmosphere of complex chemistry for stars, extended in temperature, except for carbon-rich and oxygen-rich stars on the asymptotic giant branch. There are schools that do fantastic work in actually trying to compute this model theoretically, but again here, this calculation is extremely complicated, and for population synthesis, we need a variety of spectra, and therefore, we still use empirical spectra. So, in fact, as Anna said, I got my PhD in '98, and the scope of my PhD was to try to include in a better way. That was the sentence that I was given quickly by my supervisor at the time, the contribution of the thermally pulsating asymptotic giant branch. The story tells that when I started to calculate this model, people have included some asymptotic giant branch, but just the early phase, before the start of the pulsation. That's quite easy to model in stellar tracks, but it doesn't contribute much at all to the energetic. So it was there, and it was not too complicated. The TP was complicated, and what I've done at the time, and I need to be said this, was to use Magellanic Cloud clusters, and I've seen Eduardo Bica in the audience. He is one of the pioneers of using these observations in order to understand and calibrate my theoretical prediction. And this is the seminal plot out of which there has been a lot of development also by other authors, which essentially plot on the y-axis is the bolometric contribution of the asymptotic giant branch, all of it, to the total energetic of an evolving population as a function of age. The points are the actual clusters in the Magellanic Clouds that are grouped essentially by age. I don't want to go into that detail, but it's essentially an age things. And what you see is that very young clusters, so these type 2 and 3, do not show much of this asymptotic giant branch at all. All the clusters also not, and there are good theoretical reasons to understand both. And right in the middle, instead, there is an increase in this contribution to about, for only the TP-AGB, 30%, for the total, also 40%. Errors there that have been evaluated at the time of this work, so 98. So what happened in the community working with these things? There are elements of consensus and elements of disagreement. The consensus that we all took was the AGB cannot be modeled fully theoretically, so we need to be creative in that. And that's mostly because of mass loss, and that is still true. The energetics, in particular, need to be calibrated with data. The disagreement is how we do this calibration and what data we use. And so there have been essentially two schools of thoughts. The one that I started, because I actually started this topic, entailed using globular clusters, individual globular clusters, and their ages. And the globular cluster that display the AGB are in the Magellanic Clouds. The one in the Milky Way are all too old, or they are open clusters. And in this sense, it's very difficult to get integrated contribution. Conroy and Gunn have actually reprised the same, adopted the same method. So for this calibration, as you can imagine there, it is essential to have robust globular cluster ages, or in other words, the calibration itself depends on that. The other line of thought by Paola Marigo and Leo Girardi, that I realize now also Leo Girardi come from Brazil, and also Brusoil and Charlot, was instead to use the population of field asymptotic germ branch carbon and oxygen stars. It's another idea, another philosophy. The complication there is, in order to simulate that population, you need to assume a star formation history. Still, for globular cluster, their star formation history, I would think, is simpler than for the field of galaxies. So I would still stick to the first option, but this is to give you what happened in the literature. So if you do this exercise, then you come out with the two different types of calibration of the bolometric. To the left, you see the classical output that I had back in 98, and to the right, the one calculated by Brusoil and Charlot 93, and you see the bolometric up there. The meaning of the line style indicate different stellar phases, but essentially this plot shows you what I already told you. The forecast in my models is that the AGB would be dominant at intermediate ages. The forecast in the other model is that the AGB, you see that little bump. I'm very sorry that I cannot use my cursor for a reason that I really don't understand. Anyway, you see that there is a bump a bit shifted in age, and that will depend a bit on the stellar track adopted. So this was the state of art. So what happened 20 years ago is, because here we have the energetics, and at the time I calculated colors, but if you want to perform a redshift evolution, you need to have the full spectral energy distribution. So what I've done 20 years ago was to include in the spectral energy distribution also those interesting stellar spectra from carbon and oxygen-rich stars, empirical, that I actually showed you earlier. And if you do this and you compare with the theoretical spectra available at the time that you see in this plot, namely Brusoil and Charlot, Pegasus, Starburst 99, these are all well-known authors of theoretical population model. At the ages where the TP-AGB phase should be important, at least in my model, I noticed a large discrepancy in the near-infrared flux, but also, and this is the thing that, as I will show you, we now see at high redshift, in the specific of the pattern of absorption features in the near-infrared. And that's due to the fact that carbon and oxygen stars have those deep bands. And so if you include them with some energetics, this will result in the integrated spectrum. I should have said I'm showing here a population of 1 billion year with solar metallicity, where the two red lines are my models of 2005, including the TP-AGB contribution, and the bumpy one, and without it. And that's a smooth line, not too far from the other models. Now, besides having a different influx, as I said, the strength of this model, I thought, the fun of it is that you can see in the integrated spectra, these molecules, CN, TIO, even C2, that you would not be able otherwise to see. And because the prediction is that they should be relevant in a 1 billion year population, this immediately suggests that redshift galaxies could actually be the one showcasing this at the best. And I will come to other work later. So we said already this 20 years ago, we actually applied for time, but it wasn't granted because the models were too speculative. That was the comment of the TAC, which I still would like to. Well, anyway, that's what the theory was saying. So people started to compare this model with galaxy data. And this is the very first paper that appeared back in 2005 using both HST data, that are the 3 big points that you see to the left, and the Spitzer data, the Spitzer satellite launched in 2004, so freshly done for this work at the other 3 points. These authors compared for this galaxy with spectroscopic redshift 1.1, the SED, the prediction fitting with my models that in this plot are the blue ones. And the red model are the classical Bruce-Wallen-Charlot 2003. And what they concluded, is not my conclusion, is that obviously without the TP-AGB in the models, you cannot fit the near-infrared data. Interestingly, this was the seminal paper that actually gave all the sound to the science we were doing. And the data are still there, actually, and should be refit. But in reality, when you fix the redshift, there isn't much degree of freedom to move in the SED. But anyway, this was one of the results. Another results come from Cimatti et al. Why this is also relevant, again, because it's spectroscopic redshift, and these are many galaxies. And we are going up to redshift 2. So redshift 2, so we're going to a redshift, and again, the data points in this plot that I'm showing you are the black points that you see that they actually scatter pretty high in the near infrared. This author, again, put the models, the blue are my models, the red is BCO3, the green are where a modification by Bruce-Wallen-Charlot of the BCO3 model in order to increase the TP-AGB. And then you see that actually you need this type of things to model the near-infrared data. In the same year, a bit later, however, there was another paper that you see here on the left by Crick et al., essentially finding the complete opposite conclusion, namely that actually, high-redshift galaxies do not support a strong contribution from the TP-AGB. On the opposite, the BCO3 model would fit much better to the whole wavelength range than my models. The difference with this work is that it is based on photometric redshift obtained with Bruce-Wallen-Charlot models, and photometric redshift is the distance, essentially. And also, it is based on priors on the star formation history of the SED. I say these things because I think when you interpret galaxies, you should neither use priors, and also, if you use photometric redshift, you need to stay within the same theoretical models. So this work appeared very convincing, surely to a certain part of the community. However, there are these caveats, and especially the 2 work that I'm showing you in this plot have never talked together, in the sense that the galaxy, the spectral galaxy from Cimatti et al. Have not then been included in this work and the other way. So let's say there was a lot of confusion. But, you know, I did this work back in 98. How many years is now? A lot. So you can revise, especially that of globular cluster revised. And so this is what actually Conroy and Gunn did, using a different sample of globular cluster in terms of ages, and also weighing the globular cluster, the individual contribution of them in a different way. And what they show is the plot to the right, where you see the V minus K of the integrated color. Yes, did I see something? Is there any question? No. Okay. As a function on age, the blue being my 2005 models, the 98 models, and you see that what they have done was to shift the model to older ages, like peaking the TP-AGB at 3 billion years, roughly. and also suppressing it a lot. The diamond in that plot are so-called superclusters, where essentially what they have done was to weight individual contribution with some stochastical fluctuations, which is absolutely legitimate. The age is a different thing, and now I will tell you what we did. So, very good. In science, you need to update your models, and this is what we have done in 2013. I wanted to say also, but note how important it is to know stellar physics, because essentially this plot demonstrates that the ages you obtain for galaxies at high cosmic time ultimately depends on how well you know the ages of local stellar population. I want to stress on that. So in 2013, we have recalibrated our models, adopting a completely new set of ages that in the meantime have been calculated. Changing tracks, we now, for this work, we adopted Padova tracks with mild overshooting. My classical work was no overshooting at all. Again, one thing that can be debated. We also performed this stochastical fluctuation calibration, finding what I show in this plot. So this plot is the analog of this, however, with our calculations. So you see the big square, the points are what are our average with the new data of globular cluster in the Magellanic Clouds, obtained and published in Noel et al. By Noelia Noel, especially Laura Greggio. They took care of all the part of the data. And what the red data suggests is actually a sharp increase still, as I predicted before, of the AGB contribution, peaking still at 1 billion year and not at 3 billion year, as the other two authors instead forecasted, with a transition occurring at 0.6 giga-year. This is important because this is a physical parameter we put in. The stochastic fluctuation has much larger error bars than the blue diamond, and in fact, the initial models are still compatible within the error bars. But let's say we have recalibrated, and the new models are the golden line then passed through. Remember this because I'm going to compare with all this model and the galaxy data. But because you guys, or some of you are knowledgeable of globular cluster, I want to explain how we explain this different in ages, because 0.6 giga-year or 3 billion years is completely different evolutionary age. And the more you go to high redshift, the more these differences actually matter a lot. So what Conroy and collaborator have used are this determination of age, where, and you see from this plot, I don't want to tell you too many things, I want to be short, but essentially the age of the cluster is determined by including the turn-off, so the end of the main sequence, but also post-main sequence phases, and the minimizing sort of the chi-square. We think instead that the age of a stellar population should only be obtained by the turn-off, because post-main sequence phases depend on many other physical processes, including helium breathing or other complications, semi-convection, that are not a direct relation to age, unlike the luminosity of the turn-off, so the endpoint of the main sequence. So we think by averaging post-main sequence phases, that's why the age shifted to the right. Having said that, let me tell you now, let me come to the clue. We started with these two quite discrepant predictions, and also even changing the model as I did, still quite discrepant with respect to the rest of the community. But the discussion went on because photometry is affected more than spectroscopy by degeneracy and also fitting assumption. So the conclusion remained in the air. Why is it a 20-year-long debate? Here I show you a plot, me 20 years ago, showing my new models to Rainer Genzel at the Rimber Castle. I actually remember that moment when I show, look, this is are so different. And Rainer said, oh, he was skeptical, but he was quite astonished. So that's why I call it a year-long debate. Now, thanks to these people that I really want to thank a lot, especially Emanuele Daddi, who is the principal investigator of this project, and Xin Lu, who was his PhD student to work out the data. Actually, these people have found the galaxy in the James Webb archive, already observed by a completely different group, that actually, as I will show you, clearly shows the features of the TP-AGB unequivocally and is able to set robust constraint to the model. This is a paper that we published in Nature Astronomy in 2024. So that's the spectrum. The spectrum is amazing, I would say. Remember that this is actually one galaxy, so we are going back 10 billion years in look-back time. The quality of the spectrum is so incredible that it is actually creating problems to models in general. So this quality is better than you can get with the Sloan telescope at redshift 0. It is incredible. The error on the observation is the distance between those two lines. If you listen to me, I can tell you we fit the model and we keep doing because we have now an extended sample of galaxies. But to gain precision there for the model are naturally less precise. Let's go to that. So what do you see here? First of all, this is the actual real face of a 1 billion year roughly old galaxy. The spectrum is from the, you see the observed wavelengths on the x-axis bottom, but also, unfortunately, I'm covering it, the rest frame wavelength up there. I really don't know how to remove that, though. I can't. So you will have to do the division by 2 and to obtain your rest frame wavelength. This is essentially analog to this plot. That's why I put it there. So you see all these bands, and I will tell you how we have actually identify them, that are actually suggestive of evolved stars, to say the least. Then in practice, several of these bands are actually univocally suggestive of the TP-AGB. This is all done in the paper. We don't have the time to discuss this all now, but please admire detection of many things, including the possible first detection of the zirconium oxide, a complicated molecule. Sorry. So the first things we did in the paper was to simply compare two stars, just in order to make sure, you know, the redshift is spectroscopic, but still that the detection are actually real. And you see to the left, the carbon star spectra, and to the right, an oxygen-rich spectra. We use the same spectra that are input of the model, just being at the resolution of the James Webb data, and you see the identification of several molecules. And then we compare today to the population model, and this is the main result of this paper, right, to my taste. So to the left, the blue and the green lines are TP-AGB, as they are called in the literature, strong are the MO5 model, mild are this M13 that I have revised, but still showing a lot of features. And then to the right are the weak or light models, so BCO3 and Conroy class of models. You see that even before doing the fitting, which you will do, you will put your dust, there are a lot, the star formation history, a lot of parameters, but you immediately see that the weak models do not have many features at all. So it's going to be very hard in spectroscopy to actually fit the data properly, especially the yellow line there. While you see that the other models have intrinsically these features. To cut the long story short, we did perform the fit, and here you have some chi-squares and the mild, so my model 2013 have the best chi-square. Now this in SED fit, but also in spectral lines, as suggested by one of our referees, to which we are very grateful. So we actually could could actually prove that. Now, note that the MO5 that has a lot of TP-AGB, in this plot it doesn't show well, but this is not due to the TP-AGB, but that shift of age, 2.6 giga, where actually the onset of the phase in the older calculation with no overshooting was 100 million years. So in reality, the MO5 still can match most of the feature, even better, but there is an offset in age by which the star formation history of the MO5 is different. I want to stress that. But this is important to understand the rest. Stimulated by many referees, we also used many other models, including EMILES, that has a bit of TP-AGB, possibly a La Padova tracks, but not using TP-AGB spectra. It's not very clear, but also unpublished version of BCO3. But essentially, the conclusion is the same. Most strikingly are the latest X-shooter-based models by Verro et al. And they actually release one of the worst comparisons, in spite of having all the phases treated empirically, rather than, as in my case, having the TP-AGB empirical and all the rest was fully theoretical, which we can discuss this. We don't have the time now, but again, reinforces the fact that you need to have a correct energetic, calibrated properly, and then use the proper spectra. This is how I would interpret that. Now, we are in Brazil, and I have meeting Rogério and Miriani Pastoriza many years ago, actually, so it is not true. And this, I have stressed in the paper that we were the first to see the feature of the TP-AGB. We have been the first to see at that detail at high redshift where their strength is maximum. And I will explain you this in a while. But I need to emphasize and acknowledge the work by Rogério Riffel back in 2007, to which I participated at least one of those papers, who actually, Rogério already told the world that there were absorption feature that you cannot fit unless you pump in some thermally pulsing asymptotic germ branch. Riffel also did a very useful paper in 2015 in this respect, and also I would like to acknowledge another paper by Lucy Mara Martins. So, all in all, there were already a hint, but the community was completely transparent to that. And now we see whether the big galaxy high redshift convinced. So why high redshift galaxies were the target of our initial proposal in 2004? Well, simply because the TP-AGB is a phase that developed quite early in the lifetime of a population. If you accept that the biggest galaxy form at high redshift, as we think they did, well, then 1 billion year, you end up at redshift 3, 2, or 1, or that, let's say, according to the age of your galaxy. And this is a plot that shows you what stellar phases are important as a function of redshift. It gives you the advantage that all the stars in your galaxy will go in the same evolutionary phases together, which amplify your signal. That was the first. And in fact, this is what we are seeing, because essentially that galaxy that we fit, independently of what model we use, turn out to be basically passive, quiescent, and with an age around 1 billion years. Now, I will use my own work, but this is well-known work. Why then we went for massive galaxies? Because we think they are the one forming first in the universe. And this is a quite famous plot in which we show the fact that you see this workout with long galaxy, but back in time, as a function of galaxy mass. The mass is labeled on the Gaussian. The star formation rate, which is the y-axis, as a function of look-back time, peaks at high redshift for the most massive galaxies, while lower mass galaxies keep having a smaller amount of star formation, so lower level of star formation for a much longer lifetime of the universe. Therefore, if you want to have this stellar phase emphasized where all together, then you will go for massive galaxies. That's why Emanuele Daddi went into the archive of the James Webb to look for massive galaxy that could be quiescent, and indeed he succeeded. Now, maybe you all... Yes?
Yes.
Yeah, I'm basically finished, but this phase is not just a theoretical pleasure for all of us doing stellar evolution. The thing is, it affects the ages of galaxies and hence the stellar mass that one obtain. In this plot, we have already, many others did this exercise, but essentially if you have an SED that becomes red at younger ages, your ages, fitted ages will decrease, the stellar masses will also decrease. Now, there is a recent debate on this impossible galaxy that the James Webb Space Telescope is observing, and I think, and this is what we are working on now, it may not change the thing, but effectively, it may well be that ages and masses of these redshift galaxies are overestimated, at least a fraction of it. Now, I'm just showing as a theoretical speculation before concluding a plot in which you have the space density of this massive galaxy as a function of their stellar mass, as a function of various cosmologies, and here they put the two detections with errors on the y-axis, but not on the x-axis. But I took the freedom to add an error on the x-axis, and maybe this galaxy would not be intentional. This is really pushing the results. However, remember, ages and masses are not something intrinsic to the galaxy. You obtain it with the models you apply. So your choice of models will tell you how galaxy evolve. Very briefly, I want to do, this is all, now we have 10 galaxies more, still from the archive, and they all consistently find the best fitting model and all consistently find lower masses and lower edges. This is what Xing Lu is doing. I don't want to say anything more than that. And please find my summary. So my happiness before I get retired is that my 20 years old prediction, after all, was confirmed by data at high redshift. This makes me very happy. Now, being a modelers, now we want to improve on that chi-square by actually manipulating the models, but the signal was clear. You need that phase, possibly with the energetic and onset time that we have calibrated in 2013. Thank you very much, all of you.
Thank you, Claudia. Questions from the students? Oh, we're going to get passes. Questions from... Go ahead. Are there questions from YouTube or?
Hi, Claudia.
Hi, Rogerio.
Thanks for the very nice talk. So I'm glad to see these very nice results. Your models on 2013, they seem to be most accurate than 2005, okay? So you only changed the energetic in those models regarding the 2005, and how does this affect the masses you are determining? Like how many %?
Yeah, so with respect to the 2005, I changed the energetic, but also the onset age, following the recalibration of ages of globular clusters. So the TP-AGB now is a sharp feature, but should start around 0.6 giga-year, according to those models. Back in 2005, I had a start age of 0.2 giga-year. Now, 400 million years can die in the error of ages of globular clusters, which I think, however, they are very accurate now. But at high redshift, it matters. So let's say there are two changes that I did, the onset age and the energetics. In this Capozzi et al. 2016, we tested all the models, also the M13, and the masses changes a bit less than this plot with respect to MO5, but you have still 0.2, 0.3, depending on the galaxy. It is in that paper, and you will see the actual effect.
There are some questions from this that's online. So there's one. How do you compute the ages of the cluster? I think they're the star clusters.
Yes,
And,
yeah, okay.
Comparing to theoretical isochrones.
Yes, I didn't compute the ages in neither of the cases. In my seminal work, I used the ages by Searle, Wilkinson, and Bagnolo, and they used the luminosity of the turnoff with theoretical tracks, yes. Only up to the turnoff, and the error in age you see in this plot, that reflected what was available at the time. I adopted their calibration. In the latest, we used a set of ages, probably De Angeli or some other database, where all the clusters have been fitted with isochrones only up to the turnoff, with the latest Padova tracks at the time with mild overshooting. So I can tell you why this was the choice at the time, because we wanted to use the exact same age framework that was used in by Conroy and Gang, who were actually changing this time. But as you see, the results are different, and I explain why. We only use turn-off ages, while they actually use post-main sequence ages. I hope this answers your questions. All the details of the age calculation are in the paper that I quote.
There's another one. Why do you think X-shooter spectral libraries, SSPs, cannot reproduce well?
That's a very good question, and I really don't know. Let me tell you what I see. I don't want to speculate because I haven't yet used those spectra. What we obtain by fitting is written there is a very old age, a low metallicity. So somewhat the partition, it may not be the X-shooter in spectra, but it could be the type of synthesis that Vero et al. Performed. If you give too much weight, well, actually, I could take back the pig. If you weigh too much the tip of the red giant branch, for example, too much in terms of the evolutionary lifetime along the tip is very rapid, you tend to overweight that phase. So it may well be, that the evolutionary synthesis is the problem there more than the X-shooter spectra, something I can tell you after I will use them myself. My model relies on the fuel consumption, and I would like to stress that this is quite good because it gives me a sense of how much energetic I put on the phases. But having said that, I don't want to speculate because I really don't know much about this model from the inside.
So I do agree with you with the answer of the last question. So I think it's a problem in how Vero has weighted the phases. So she used like a mean value for depending on the phase and did sort of a mixture when doing that. Okay.
Yeah,
so my other question is like, so when you're fitting a galaxy, so all ages somehow they are important, okay? Because you don't have any prior of your galaxy spectrum when you start fitting it. In your 2005 models, correct me if I'm wrong, you used this empirical spectrum just for the TP-AGB phase and not for the older phases, okay? And somehow I used a lot your model, so somehow I had this feeling along the time that due to the fact that you were using empirical spectrum for one specific phase, when you were doing the stellar population fits, this phase was chosen by the fitting process because the features, they actually were there because they were from real stars, not from model stars. So do you have any plan to include, like, for the older ages, empirical spectra of stars?
Yes, I do have, and I have already quite a lot of models that I could actually send you. Yes, life is not that simple in this sense. I mean, I have already published the models based on the Miller's library, on STELIP, and so on and so forth. You know what the problem are there? The stellar parameters that you associate, which again rely. And it's not trivial. And I wanted to say, maybe the problem in this work is also the stellar parameters. For the TP-AGB part that I use in MO5, that was relatively straightforward because we knew those were carbon and oxygen rich stars, right? There was no ambiguity. But when you have a set of empirical spectra, you need to make sure, for example, it's a dwarf and not a giant and things like that. So stellar parameters are a critical point of empirical models. But having said this, I'm using the IRTF that you know very well. You pointed me to that. So very soon, in fact, the proceeding of our work is to try to fit and see whether we can improve the chi-square with my models by adding the empirical spectra for the other phases. In a few
Horacio has a question. He's coming.
Hi, Claudia.
Hi.
How are you? In 2005, we published a paper on the nucleus of the Seyfert-2 galaxy NGC 1241. And we concluded that the colors J-K can be explained by the superposition of 25,000 AGB stars and 500 carbon stars, provided that the population is similar to that of the LMC. My question is the following. Could it be possible to, because at that time, we didn't know your model, actually, 2005.
Yeah, it's the same year. Yeah.
Possible to explain the same thing with the TP-AGB stars?
Yeah, it's fantastic what you're telling me. I already took notes because you essentially have counted the stars. Yeah, in principle, the energetic should give you a prediction of numbers. Yes. So I will look at your paper after the seminar and get back to you.
I will send it to you the reference.
Yeah, please do so. Yeah, please send it to me. It's fantastic. Thank you very much.
Great. Do we have any more questions? So maybe one last one, thinking more about the future, and there's a lot of data from James Webb that's gonna be in the archive, and it's already there. And given that, for instance, this X-shooter spectral library doesn't really fit, and because of different fits people are doing, what do you think should be improved in terms of methodologies for this kind of work?
So, thank you. So this was a filler in the archive, not even our data. And also these are data that, sorry, the last one, apologies that I go. These are still archival data. Plus we have our own accepted proposal with more galaxies. This will improve the statistics, although the spectrum that I show you is already a killer because the signal to noise is 100. I mean, it's incredible. Regarding the X-shooter, I showed that those population models based on X-shooter do not work, but I still do not know whether if I use the actual spectra, obviously I don't want to offend anyone, but this is the outcome. It may well be that those spectra are useful, the X-shooter spectra, but there aren't many AGB stars there. So this could be another problem. So moving forward, it would be great to increase the database of full spectrum as much as possible. The latest IRTF started at 7,000, but you also need the optical. So full observations of a wider sample of stellar species, because for the galaxy you need that, including, and this is something I already discussed with Rogerio, hot stars, because you need, the more you go to high redshift, the more you need, population gets younger. So you also need A and B type stars. There are, of course, some HST-based libraries. One is called Ulysses, but they are in different wavelength range. On the other hand, I'm quite confident that my recalibration of at least that phase, that works. That would be great, because if we can close that chapter, we can work on different things. There are other problems in stellar evolution. The overshooting is one of them, where possibly this data now, this awesome data that goes over the wavelength range, will allow us to calibrate. That's what I would like to do in the future.
Is there no more questions? Let's thank Claudia again.
I thank you very much. Yeah,
Claudia.
thank you very, very much. And I hope our path will cross again at some point.